In this video, we're going to start talking about numbers, and we're going to have two main types of numbers. We're going to have exact numbers, and we're going to have measured numbers. And before we get into the difference between those two, I want to talk about three parts that all numbers have. So there's three parts to every number. The first part is the magnitude itself. So is it 3? Is it 7? Is it 64.2? Is it 0.000001? What is the actual numbers, right? What is the magnitude of that? The second part is our uncertainty. And our uncertainty is going to be shown by the number of significant digits. So SF for significant figures, significant digits, same thing. And we'll talk in a lot of detail about that coming up here real shortly. And then the third part is our unit. So 3 what, right? 3 centimeters, 3 inches, 3 miles, 3 apples. If I just say the number 3, what is it that we're referring to? So what's the actual number? The magnitude. Our uncertainty, which we're going to show using our number of significant digits, and then our unit. What is it we're actually talking about? When I grade problems in this class, you're always going to get graded on all three parts. If the answer is 42, and you get 42, but you put 42.00, and it's supposed to be just plain 42, you're going to lose points because you're saying it's more certain than it actually is. And if it's in centimeters and you just leave off that unit or you put the wrong unit, you're going to lose points for that also. So I'm always looking for all three of these. What is the actual number itself? What is its amount of uncertainty? So are your significant digits correct? And then what are the units? So three parts to every number. Two main types of numbers. The first one are exact numbers. And exact numbers are actually just that. They're exact, meaning they have no uncertainty. So they contain no uncertainty. In general, the more significant digits you have, the more certain the number is. So if these have no uncertainty, then they have an infinite number of significant digits. Right, we want them to have as many significant digits as possible, and that's infinity. So they have an infinite number of significant digits, or significant figures, thus the F in my abbreviation. And exact numbers, these guys are going to come from counting. Or definition. So there's 7 days in a week. There isn't 7.002 or 7.00, right? There's exactly 7 days in 1 week. It's not 6.999999. It's 7, exactly 7. No uncertainty whatsoever. If I asked how many significant digits are in that, you would tell me infinity, right? That's the number that it would have. Counting. Not that you can see me right now, but the number of teachers sitting at the desk here, there's one of me, right? There isn't 0.997 or 1.004. There's exactly one instructor sitting at this desk. So these guys are going to come from counting or definition. And we are going to encounter some exact numbers in this course. The second type, and the one that we're going to encounter more often, are measurements. So measured numbers. And measured numbers always contain some uncertainty. They come from measurements. I guess that should be obvious. And they always contain some uncertainty. And again, the number of significant digits are how we're going to show that uncertainty. And again, I promise we'll do those soon. But just kind of an example here for a measurement. If I was trying to measure something in this graduated cylinder, I'm not really good at drawing here. And this is a 1. This is a milliliter graduated cylinder. And this is a 2. And my meniscus is here. And I was to read this, whenever we're reading something, right, whenever we're taking a measurement, we always include the number of digits that we know for sure. So I know for sure it's 1 because there's a 1 there. So I'm going to include that. And then we always include 1 estimated digit. Never more than 1, never less than 1, always exactly 1 estimated digit. So I'm going to estimate that that's maybe at 7. You might say 8 or 6. But that's that uncertainty part. So I would say this is at 1.7 milliliters. And again, you might estimate it a little bit differently, but I should have 2 digits in my number, 1 digit after that decimal point. So we're going to only estimate 1 additional digit. If I had another graduated cylinder here, and this is a 1, and then I had tick marks every 0.1. And then I had my 2, and now I put my liquid in here, and I read from the bottom of my meniscus. Again, we're always going to include the digits that we know for sure. So I know 1, and then I also know 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, and now I'm going to still include that 1 estimated digit, and I'm going to say 4. And again, you might estimate that a little bit differently than me, and that's fine. That's that uncertainty, right? That last digit is estimated. That's that degree of uncertainty. So I have 3 significant digits, 2 after the decimal point for this cylinder, right? I always include all the digits I know for sure. In this case, I knew the 1, and I knew the 0.6 for sure, and then I estimated that 4. In the first cylinder, I knew the 1 for sure, and that was it, so we estimated the 0.7. Because the second one here has more significant digits, I would say this is a more certain measurement. So always has some degree of uncertainty, right? Always include all the digits you know for sure, plus 1 estimated digit. So let's talk about that uncertainty next. So significant digits, significant figures. Sorry, it's really annoying. I always say significant digits, but then I write SF for significant figures. One of the many frustrating things you'll probably find about me. Significant digits or figures. Usually abbreviated SF. Sometimes I'll say sig figs, so SIG, FIG. So again, remember these are going to be used to express the amount of certainty or uncertainty in our number. So significant digit rules. Our first one is that all non-zero digits are significant. So if it's not a 0, it does count as being a significant digit. So if it's not a 0, it does count as a sig fig or a significant digit. Where it can get a little messy is zeros. So not all zeros are actually significant. So zeros that are between non-zero digits, so called confined zeros, are significant. So confined zeros are significant. So confined zeros, again, are zeros that are between non-zero digits. So for example, 106. That 0 is between the 1 and the 6. The 1 and the 6 are not zeros, so they are significant. That 0 is between the 1 and the 6, so it's confined, so it is significant. So this would have 3 significant digits in it. So 3 sig figs. There could be a couple zeros, 20064. The 2, the 6, and the 4, again, are significant because they're not zeros. Both of those zeros are confined, so they are going to count as being significant. So this has 1, 2, 3, 4, 5 significant digits in it. So 5 sig figs. Zeros that come before all other non-zero digits are not significant, and these are called leading zeros, the ones that come at the left of the number. So leading zeros are not significant. They're essentially, they tell me the magnitude of the number. So if I was to write 0.01, the 0 after that decimal point, but before the 1, right, that's my leading zero, that just tells me that this goes out to the hundredths place. It actually tells me the magnitude, not the certainty. So this would have one significant digit, 0.000007. Again, those zeros that come before non-zero digits are not significant. So this, again, only has one significant digit, right? All of these here are not significant. Only the 7 is. 0.002046. So this one, these leading zeros here are not significant. Leading zeros are never going to be significant. But the 2, the 0, the 4, and the 6 are. Right? That 0 between the 2 and the 4 is confined, so it is significant. The 2, the 4, and the 6 are not zeros, so they're always going to be significant. So this has 4 significant digits in it. Our next rule has to do with trailing zeros. So these are zeros that come after all non-zero digits. So trailing zeros are significant if, and it's a big if, there is a decimal point. And not significant if there is not a decimal point. So they are significant if there's a decimal point. They're not significant if there is not a decimal point. So examples for us. Oops, I want that. If I was to do 10.0, because of that decimal point, that makes both of those zeros that are trailing, right? Both of these zeros here come after my non-zero digits, so they're both trailing. It's going to make both of those significant. So this has 3 significant digits. If I was to just write 100, no decimal point, this is actually only going to have 1 significant digit. Only the 1. These 2 zeros are trailing digits, but remember they're not significant if there isn't a decimal point, so just 1. How about 102.00? So what do you guys think? I'll let you do this one real quick. How many significant digits are in that one number? I hope you guys came up with 5. Right? The 1 and the 2, obviously, because they're not zeros. This 0 between the 1 and the 2 does count because it's confined. There is a decimal point, which means those both count. So all of those digits are actually significant. Here's another one for you. 0.000740400. So how about this one? How many significant digits in this number? I think we're using all of our rules here. Yeah, let's go through this one together. So these guys here, these are my leading zeros. Those are not going to count. You have to have them. You can't not write them, because if you don't put them there, your magnitude is wrong, right? 0.007 is different than 0.7. Those are not the same number. So they're important to write, but they tell us the magnitude, not the certainty. We don't want our magnitude to be wrong, so they have to be there. The 7 count, sorry guys, the 7 counts, this 4 counts, this 0 counts because it's confined, this 4 counts because it's not a 0, and then I do have a decimal point. These come after, they're trailing, right? They come after that decimal point. So they come after all the non-zero digits, and there is a decimal point, so they do count. So this one is going to have 1, 2, 3, 4, 5, 6 significant digits. So be sure to practice some of these. For sure there'll be some significant digit problems on your quiz at the end of this section. But also, every time I grade a number, I'm going to grade it on significant digits, right? Remember, I'm going to grade it on magnitude, the number of significant digits, and then also on our unit, which we still have to talk about. So before we start talking about significant digits and mathematical operations, I do want to go through rounding rules. Often when we're doing a calculation, we are going to need to round our number or our answer to get the right number of significant digits. And there's several different ways to round, as weird as that sounds, and I just want to make sure that we're all using the same rules. So these are probably about as easy as the rules can get. So if the first digit that you drop is less than 5, then you actually just drop that digit and everything that comes after it. So round down. So if the first digit dropped is less than 5, drop it and all subsequent digits, so all the numbers that come after it. Often we just say round down. We're not actually rounding down though, we're really just dropping digits. So for example, if I had 62.3436, and let's say we wanted to round this to 3 significant digits. So 3 significant digits mean I want to end it right here. So 4 is going to be the first digit that I drop, right? I want to keep 3 significant digits, and I'm just picking 3. So I'm saying to round to 3. I could have picked anything else, but I am just picking 3. So round to 3 sig figs. I need to keep the 6, the 2, the decimal point, and that 3. So the first digit I'm dropping is 4. Because that 4 is less than 5, we're literally just going to drop all of those digits. So this is going to become 62.3 when I round it. Second rule, and there are only 2, if the first digit dropped is greater than or equal to 5, round up by increasing the last remaining digit. I can spell, oops, eraser. I'm actually a horrible speller, sorry guys. Remaining digit by 1. So if the first digit dropped is greater than or equal to 5, round up by increasing the last remaining digit by 1. So for example, 62.3536. And again, I'm just going to pick 3 and say let's round this to 3 significant digits. So I want to keep the 6, the 2, and then this place. The first digit I'm dropping is a 5. Because that's greater than or equal to 5, I'm actually going to increase the 3, right? That 3 is my last remaining digit by 1, and this is actually going to become 62.4, right? Because this again, right, is greater than or equal to 5, This here, this 3, my last remaining digit, gets increased by 1, so that 3 becomes a 4. So this number rounded to 3 significant digits is going to be 62.4. And we'll have opportunity to practice this as we go through this course. But pretty straightforward. Less than 5, round down. Basically, you just drop all those digits. Greater than or equal to 5, you round up. You actually increase that last remaining digit by 1. Okay, significant digits and mathematical operations. So we're going to have a different rule for addition and subtraction than we do for multiplication and division. So significant digits and mathematical operations. And let's do multiplication division first. So our rule for multiplication and division is that our answer cannot have any more significant digits than our original number with the fewest number of significant digits. Kind of the interpretation of that is our answer can't be any more certain than our least certain number, right? Remember, the number of significant digits tells us our certainty. So if you only know one number out to the 10th place, but then you know another number out to the 100th place, your answer can only go to that 10th place, right? It can never be more certain than our least certain original number. So the answer has the same number of significant digits as the original number with the fewest number of significant digits, right? The answer cannot be more certain than your least certain number. So multiplication and division, let's do an example. So if I was to take 2.00 and then multiply it by 4.000, right? This one has 3 significant digits in it. Remember, those zeros count because of that decimal point. This one has 4 significant digits in it. So my answer, because 3 is less than 4, I want 3 significant digits in my answer. So this I want to be 8.00. Right? I wanted to have the same number of significant digits as my original number with the fewest number of significant digits. Another example. Let's do 7.0 multiplied by, 10.1. So when I do this, and let's do it without rounding first, I'm going to get 70.7. I have 2 sig figs. Here I have 3 sig figs. So I do want 2 in my number, in my final answer. So this one I'm going to have to round, right? When I do it, I have 3 there. I only want 2. So what is that going to round to using the rounding rules that we just covered? Yeah, so I want 2 digits, which means the first one I'm going to drop is a 7 because that 7 is greater or equal to 5, greater than 5. I'm going to actually round up to 71. So that would be my 2 significant digits. Just for kicks, let's do another one that's very similar. Let's do 4.0 times 10.1. So I get 40.4. This one's going to be, it's a little tricky. Again, this has 2 significant digits. This has 3. So I do want 2 in my answer. This time the first digit I'm dropping is less than 5. So I'm just going to drop it. But the problem is, if I just write 40, how many significant digits are in that number right now? Yeah, there's no decimal point. So this is actually only 1 significant digit, and I want to have 2 in my answer. I have seen some texts and people do this and just put a decimal point with nothing after it. Don't do that, please. It might be fine in lower level classes, but it's actually not the proper way to write a number. It's just kind of saying, I want to do sig figs and I'm getting lazy. So the proper way to do this is to put it in scientific notation. So if I want to write this number with 2 significant digits, I'm going to actually write it as 4.0 times 10 to the first power, or just 10, you don't need the 1 there, times 10, either one of those. So that's how I would have to write this to get 2 sig figs in it, right? I want 2, this only has 1. So by putting it into scientific notation, I can now have 2 significant digits. Again, please don't do this. If you do that, I am going to mark it incorrect. Again, sometimes in lower level classes, they'll let you get away with it, but not anymore. Sorry, this is college level chemistry, so we're not going to do that. We're actually going to do it correctly by putting it into scientific notation. I'm not going to spend time in this course reviewing scientific notation. That is something that you need to be pretty good at coming into it. So if you need to go back and review that on your own, please do. And during our weekly session, if you want to ask me a couple questions on it, that's fine. But I do assume that most of you, by the time you get to college level chemistry, can do scientific notation. So please review that on your own if you need to. So multiplication and division. Our next rule is addition and subtraction. And for some reason, this is the rule that most people get wrong. If anyone's going to lose points for sig figs, it's usually on this rule. And I don't know why that is. I don't know if it's just we don't do a lot of addition and subtraction. Most of the math that we do involves multiplication and division. But this rule, people get it wrong a lot. So just pay attention to this guy. Usually if I say that, then somehow it like sticks into people's brains. Be like, oh yeah, this is the weird one. And then you'll think about it. But this one isn't actually the number of significant digits. It's the number of digits after the decimal point. So the answer cannot have any more digits after the decimal point than the original number with the fewest digits after the decimal point. So it's not the actual number sig figs. Again, it's the number of digits after the decimal point. So example for us, if I was to take 10.03 and then I was to add, let's add 20.060 to it. So when I do this, my first number is 2 digits after the decimal point. My second number has 3 digits after the decimal point. So I want to write this with 2 digits after the decimal point. How about if I was to do 0.0001 plus 6.00497, and we're adding again. So the first number, this is kind of where folks will go astray, 0.0001 is actually only 1 significant digit, right? because those leading zeros don't count. 6.00497 is 1, 2, 3, 4, 5, 6 significant digits. So if I was multiplying or dividing these two numbers, I would only actually have one sig fig in my answer. I'm not, however, right? We're adding, so I want to have the fewest number of digits after the decimal place. So when I add these, let's see if I can do addition here while you're all watching. So, is that right? Looks right. I have one, let's get a different color here. I have 1, 2, 3, 4 after the decimal point. 1, 2, 3, 4, 5 after the decimal point, so I only want 4. 1, 2, 3, 4. So I need to drop that number. It's greater than 5, so this is going to be 6.0061 is going to be my answer. Ooh, 51, sorry. This stuff isn't confusing enough. 6.0051 is going to be my answer. And again, if I was multiplying those, I would just have one significant digit because we're adding and subtracting, right? It's not the number of significant digits, it's the number of digits after the decimal point. So this is going to be the correct expression for that number.